welcome back to Straight Fire. This is episode 15, Dilating Linear Equations. Before we even do a single question, let me just give you the main idea for today. So, when we're talking about dilating a line, if the center of the dilation is on the line, the answer to the dilation will be the exact same line unchanged. And I'll talk briefly about why that happens. And that will happen sometimes. The other situation that could happen would be if we have a line and the center of the dilation is not on the line. The brand new equation will be a line that's parallel to the given line. And it will be parallel to the given line. But in this case, the answer would be placed higher above the given line. If it was reversed, where the center of the dilation was above the given line, the answer will be a parallel line pushed below the given line. Well, let's actually take a look at the specific examples, but that's basically it. So in this question, they're giving me the equation of a line. They want me to create a new one after I dilate it by 4. Most important bit of information is where the dilation is centered. The dilation is centered at the origin, which is the point 0, 0. So looking at the equation they gave me and looking at these choices right here, I know that it's a good idea to get the y by itself so that I can make the question look very similar to the answers. And if I get y by itself, I'll be able to read the slope and the y-intercept easily. So subtract 2x from both sides, and in one small step we got the y by itself. Now the next thing I have to ask myself is whether or not the center of the dilation is on the equation. And one way to tell that is to take a picture of it graphically, or another way is just to plug in the center of the dilation and see what happens. When I plug the center of the dilation in, I get 0 equals 1, which is not true. And since it's false, I know that the center is not on the line. That means I'll get a brand new equation. So I will not keep the same equation. The equation will have to change. Right now the y-intercept is 1. The center is below the line. So the answer will be pushed above it and will have the same slope. So we know that the slope won't change. We know that the slope will stay the same, and the y-intercept is going to be above it. The scale factor is 4, which will change the y-intercept. It would multiply the y-intercept by 4 and keep the slope the same. So just thinking out loud here. So the equation of line M will be parallel. And the reason why that's true is because the center of the dilation was not on the line. The slope of line M, the original or the brand new answer, will be exactly the same, -2. The y-intercept was 1, but since we dilated it by 4, the new y-intercept will be 4. So that's what you can do and should do when the center of the dilation is the origin and the line does not go through the center of the dilation. It's difficult to put too many rules down on this, but we know we'll get a brand new line because, just as I said in the opening, if our point of dilation or center of dilation is not on the line, then the answer will be a parallel line. It's either above it or below it. Let's take a look at the next one here. So we're going to change the equation to y equals negative 2x minus 1, and it says we're going to dilate it by 2 this time, again centered at the origin. And they want us to write the equation of the image. So this is more difficult because it's not multiple choice. So the very first thing is to find out, is 0, 0 on the line? When I plug 0, 0 in for x and y, when I plug the center in, I get 0 equals negative 1, which is false. So I know I'm going to get a brand new line. So my answer will not be the same exact answer, but it will be parallel to the original. So since it'll be parallel, it'll have negative 2 as the slope. The y-intercept was negative 1, and since I'm doing a scale factor of 2, the y-intercept will be 2 times as much. So 2 times negative 1 will be negative 2. And that would be the answer. And let's take a look at the last one, which, well, I've never done any of these questions before, so we'll see how this one turns out. The last question for today, we got an equation, same one as before, but this time we are going to dilate it by 2, but not through 0, 0, but through the point 1, negative 3. So let's take a look. What happens when we take this equation here and plug in the center of the dilation? Is the center of the dilation on the given equation? If we plug in the x and the y, we end up getting negative 3 equals negative 2 minus 1, which is negative 3. So in this one, we get something that is true. So it means that the center is on the line. And whenever you dilate and the center, 1, negative 3, I'll graph it here. If the center is on the line, our line is negative 1 for the y-intercept, and the y-intercept is, or the slope is 2. So the black dot there is the center of the dilation, and the white line is the given line. Whenever that happens, it's almost like taking a flashlight and putting it right on an object. If you do that, you won't see any shadow. And that's one way to remember exactly how these dilations go. So if your center of the dilation is touching your line, the answer will be the same exact line that you started with. But let's just take a look at this one a little more carefully. If we started with this equation, y equals negative 2x minus 1, and we already know the answer that if you use the center of the dilation at this point right here, you end up getting the same answer back again. Let's actually do one that's not on this worksheet. Let's actually move the center of the dilation to, let's just say this point right over here. So if I made the center of the dilation negative 3, positive, negative 3, negative 2, where exactly would the image go? Think of that as a flashlight that's shining on a line. And if it's shining on it, it's going to cast a shadow. And the shadow will be over here someplace. But let's actually figure out exactly where that will be. This is maybe the toughest of all the questions to do, is to find the exact location of an equation after it's being dilated by a point that's not on the origin and not on the line. To do this visually, you might want to use a compass or think about what a compass would look like when you're actually doing a dilation, which is something that we did in our class. But if this is your first time thinking about it that way, we're doing a dilation of 2, just as the original question said. But this time we're going to move the center of the dilation off of the line. When I did this in my classroom, I even have a poster of a spotlight in the back of my room that's shining on a Batman symbol. So the center of the dilation is the light bulb of the flashlight, and it's shining on, in this case, not a Batman symbol, but a line. And I'm going to need to find the location of 2 points now for sure that are on the line. And here's one point that's definitely on the line for sure. And we'll go with this one right here too. It's definitely a point that's on the line. Now once we turn on our light bulb, it'll shine a beam of light on each of those points. And it's important to do this with a ruler to really do a very good job. So I'll just use the computer's ruler to create that beam of light. And let me do that again, shining that light. It takes me a little while to do this just the right way with the computer. Aha. So that's pretty good. Well, it's got to be perfect. That'll do. Alright, so that's where the beam of light is shining on both of those blue points. And if you think about how the dilation does work with a compass, if we don't move those points at all, it's considered a dilation of 1. So if we opened up a compass, that would be 1 swing of the compass. If we're doing a dilation of 2, we want to repeat this swing right here one more time. So if you follow the pattern of, since we're not using a compass, if you just follow the slope, it's going up 1, 2, 3 over 2. If you open up a compass again and swing it again, 1, 2, 3 over 2, the compass would swing outward this way, locating our dilation of 2. If you wanted to repeat it again and do a dilation of 3, you could do that again, but we'll just stick with our dilation of 2. We're going to do the same sort of thing here visually. So we would open up our compass and swing once to make a dilation of 1, and swing it again to make a dilation of 2. Since we're not using a compass, we're just going to use the slope. So the slope is down 1 over 1, 2, 3, 4. So down 1 over 1, 2, 3, 4 puts me back on the line. So you can picture a compass swinging once and then swinging a second time to locate that point right there. So these 2 points right here will be the images of the original 2 points, and if we connect them with a straight line, we'll get the shadow which will be our answer. And let's see how that works out mathematically. So does this equation here have the same slope as the original? This slope was -2 over -2. Taking a look at the pattern here, it's down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. So that equation definitely has a slope of -2. And then finding that y-intercept is important for me. The y-intercept changes to 1. Well, the y-intercept was down here originally at -1. Now it's at 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. And once again, this last question was my attempt to try to give you an example that would be probably the toughest of all sorts of questions to deal with, when the center is not on the line that you're given, and it's also not on the origin. So it takes some careful planning to figure these things out.